Hello there. Welcome to another one of my projects that I've been working on recently. And this project is a project about time series forecasting. And basically, it's about Romanian energy consumption and production. So, it's actually going to be mainly based on the consumption part, but there's still some elements of the production and the different flow types and that kind of thing. But basically, the whole point of this project is to show you how I did this project using a ARIMA model to do a time series forecast. And it's just going to be forecasting the consumption of Romania from 2019 till part of 2025. So that's what this whole project is about. So let's get into it. Now, the first things first, import our libraries. I had some issues with this, a lot of issues. I do recommend that you do this in a virtual environment because trust me, this thing can give you some some problems. Can really make you annoyed. All right, so I had to do this in a virtual environment. I'm not sure I'll be able to show that, but yeah, let's move on. So the next part that I did was to import my data. So the data is from Kaggle. I found it there. I tried getting the one for 2026, but I think there was a problem with the data portal or something like that. So I just used the one from Kaggle, and that's what I went with. Okay, so we this is what our data looks like. We have our daytime. So if I do this till let's see till so you can see that this is from 2019, first of January 2019, and that's from is that 12 a.m. or okay yes that's the first hour of the day. That's one of the things that usually confuses me sometimes. But this is 1 o'clock. This is 2 o'clock, 3 o'clock, and it's actually an hourly data. So you can see that the end is going to be till I think late 2025. Okay, no, it's early 2025 actually, which is March 19th. Yeah. So this is on the last hour of the 19th of March 2025. Okay, so let's just change this one to head and let's move on. Okay, so first things first, we're just gonna do some basic things. This one shouldn't be too difficult. Just checking for if there are any missing values. When I checked the last time, there weren't any. So we can see we have 000 all through. Now, the next thing we do is we just want to take a quick look at an overall view of data. All right, so we have our consumption here. Quick disclaimer, the data set that you can see here, everything is in megawatts. So this is 6,000 megawatts, and this is 6,116 megawatts that was produced at this time. And these are the different flow types that we have. You have the renewables and the non-renewables, with the renewables being that should be wind, hydroelectric, and solar. So you have the other non-renewables, which are nuclear and the others. So these are in megawatts. I hope I put them in the graphs that I put. Anyways, I'll probably just update it when we get there. All right. So this is a brief summary. So we have about 54,170 rows. So we have the mean, we have the standard deviation, interquartile ranges, and we have the maximum values. So, um, another quick disclaimer. There are some of the instances where you see the other one of these being minus. I think that should be the production. That should be the production. So there are some instances, if you explore this data by yourself, you see there are some instances where you have a minus. So what that means is Romania at that particular point in time borrowed electricity or imported electricity. I think that's a better way of putting it. So they imported electricity, and that's why it's a minus. But for all the but for all the times that it's like this, then we can say that that Romania used their own electricity or they exported it basically. But for the instances where you see minus, they just borrowed electricity from I think probably one of the neighboring countries or something. So that's about that. We can just do about info to check some things. Okay, and one of the things that could also annoy you is the whole date time thing. So I was changing the index and changing the type of the datetime column because of some problems I was having. Basically, I just had to be changing it regularly, but I changed this to datetime format. So as we can see, let's do that. Okay, so we can see here that this was objects. This was objects. That's how it was. And right here, you can see that it's datetime. So that will help us with the plotting and with some other things. Okay, so straight on, we're just going to quickly explore the data and see what our numbers are. All right, so let's see what the total consumption and production are for the period of 2019 to early 2025. And that's this right here. Okay, that's 3. Okay, so that's 353 million kilowatt. No, sorry. 353 million megawatts, which is about um how many gigawatts now? Well, yes, you can always change the units. I think the gigawatts would be 10 raised to times 10 raised to power 3 of megawatts. That's 1 gigawatt, basically. So this is the total that we have. It might be, I think it's going to be better if we can see this in a graph. So what I did, I created a donut chart. Okay, so we have this, and so they consumed more than they produced. Okay, which is not so horrible. So probably they just imported electricity, just sometimes in the year. And as long as this is not like, let's say, 70 or 80 or something like that, then I think this is quite fair. If you have another opinion, you can always put comments. But this looks a bit balanced. It does look a bit balanced. So 50.6, 49.4, not bad. Not bad, Romania. All right, so next thing, we're going to look at consumption by fuel type. So what we need to do here is, okay, we have the stock column and then we have the fuel type. So we have that. Okay, so basically what I did here was to take the data set from this guy here, because we didn't really need these guys right here. We didn't need the consumption and the production column, so I just took that one away. And yes, you can see nuclear, and these are just the 4 types. So what we have now is, yes, here we go. So it looks like we have the majority of the electricity production to be from the dams, from the hydroelectric, which is good. That's very good, actually. They were very good with their renewable energy. And wind is 12%. Solar is very low. Same with biomass. But your hydroelectric is very good here. This is 28%. That's more than the others. Well, nuclear is 20%. Because 20%, oil and gas is 18, coal is 18. But I'm actually quite impressed with this. I'm actually very impressed with this. This is good. All right. So, energy consumption. Let's see what we have. We have the figures, and for this, we'll be plotting the datetime with the consumption. So let's see what that gives us. Okay, so by the hourly data points, it doesn't look very distinct in this graph here, but this is the trend that we can see up and down, up and down, up and down. So this is a seasonal data, and to be honest, most energy data that you see, it tends to look like this because more people use heating cold in the cold in the cold periods of the year, and more people use less heating or less yes, basically less heating during the warmer parts of the year. So that's why you see these kind of trends like this. So the demand usually changes over the year, and it's usually very constant. So if you like to do some investigation, you can always check, can always see the correlation between the weather conditions and the energy consumption. But then, to be honest, I don't really think it's something you should bother yourself about because when you're cold, you're going to use more heating, which means more electricity, and when you're hot, you're going to use less heating. So that's why you have this kind of thing here, and that's especially for a cold part of the world. Okay, so this right here, we're just looking at the hourly electricity consumption in Romania. So this is looking at all the hourly data points. So that's about 54,000 of them. Yeah, around 54,000. So if we go monthly, what I did here basically was this looks distinct, right? So basically what I did here was to group them by month. So that's this right here. And to be honest, this whole daytime thing gave me like just made things very annoying for me because pandas was saying that some things were not allowed and then you had to go back and then change them, and it can be very, very annoying, trust me. Anyways, I was able to overcome that. But so here's it in the monthly. Here's this in the monthly form. So we can see it's more clear to us now. Follows very similarly to this. Looks very similar to that. Now we have the consumption, and you can see. So basically, it's the group by of the months, and we're going to be adding each month together, and then we'll be getting each of this. So I think this one here, we could say this one is, let's say, 2019 February, for instance, and that's all of the data points that was recorded in 2019 February. So that's what we have for month, and we could also do the same thing for day. We just need to change this M to D here. Basically the same code. I was too lazy to put this in a function, so bear with me. I just basically did copy and paste for this guy right here. So this is the same thing for day. It's not as clear as this, but it is a bit more clear than this. So this is the daily trend of the data that of the energy that was consumed in that period. Okay, so let's move on. All right, so now let's say monthly fall type. So I put here hourly energy production by fall type, and we can see right here. So this is the monthly. This is the monthly production of the different fall types that we have. And for January 2019, we can see that which one's bigger, oil and gas or nuclear? 308. That's 1 million. Okay. 0 to 8. Okay, so oil and gas is the largest here for January 2019. Oil and gas is the largest there. And okay, we can see different things right here. Okay, so for this one, I just used an area graph, and we can see how much they differ from each other. So the red one is oil and gas. It's quite a good amount. Solar is not really, I don't think it's really one of their strong suits. It is quite small. So we can see that it's barely visible in some during some time of the year, and to be honest, even at the highest or the most productive times, it really doesn't take a large chunk of the total production. So, but that's by the way. We can see hydroelectric here takes a lot of it. Hydroelectric takes a lot of it. The nuclear is a very big part of it, and yes, you can just interpret this. And I'm going to upload the notebook on my GitHub, and I'll put the link right here so that we can just check it anytime you want to check it. Okay, so renewables versus non-renewables. So we have this. So we have our nuclear, wind, and the others. And let's see what we have. So I put the wind, hydroelectric, and solar into the renewable column. Sorry, not renewable column, into the renewable columns list. That's this guy here. And we have the non-renewables, which is nuclear, oil and gas, coal, and biomass. Okay, quite the lineup there. Okay, so we have this right here, energy, DF, renewables, and we'll be summing them together. So we'll be summing these guys together on the column axis. So we have renewables on one and the non-renewables on the other. And from what it looks like here, the non-renewables are taking the lead. Let's see with our graph. And voila. Yes. So we have the renewables and we have the non-renewables, right? So let's see what we have here. Okay, yeah, basically since 2019, the renewables have taken less of the total production. Well, to be honest, it is going to be very likely. The non-renewables in most instances are going to you tend to produce more when you use the non-renewables than when you use the renewables. It's To be honest, it's a matter of efficiency. The non-renewable energy sources are usually more efficient. I mean, they're not friendly. Some of them are not friendly to the environment. They're not too friendly. Nuclear is quite friendly, but the others they're not too friendly to the environment. But they do give you what do you call it now? They do give you a high efficiency. So, but then you have a lot of countries in Europe. I think Romania definitely should be another country that's trying to get to this too. Romania and other countries in Europe. So Romania and the other European countries are usually looking to achieve net zero. It is going to be difficult, but there have been some positive signs so far. So we get something like this. Before, I think you'll be seeing something like this red, like taking like 80% of the whole bar. But then this is showing that there's progress. It's showing that there's progress over time. Okay, so that's all for our exploration. So the next thing that we have now is using our ARIMA model to do some forecasting. Okay, so basically this one here, I think I'll just put a comment here to make it a bit nicer. So we'll just be splitting this into training and test sets. Oh, let's put that there. Let's take this one away. Splitting into. Let's get the English right. Okay, so splitting that into training and test set, and it's saying I'm just going to use 90% of our data to. We're going to use 90% of our data to do the training set, and anything that's not part of the training set is going to become our test set. That's what this little guy means right here. So anything that's not part of this is going to be our test set, and we're going to have that. Okay, so if we look at, let me just see. So if we have len df, let's say train here, we can see the difference. Okay, that looks a bit small. So So we have 68, and then we have 7. Okay. Yeah. Okay, I guess we don't really have a lot of months. If this was the daily consumption, then we'll probably be having like I don't know, I think about we'll be having double, no more than triple this size. I think we'll be having something like 5,000. I'll need to change this one to daily consumption to be sure again. But this is monthly consumption. You can only have a few months in that period, which is about um I think 17 months or something like that. Okay, so let's go move on. So I'm gonna be setting the index to be daytime because when I did this, this is what it looks like now. So I want this to be my index, for reasons that we'll see later. Okay, so let's get that one out of the way. All right, so just so that I can see. Okay. Okay, so that's our index now. Makes it look nicer. Okay, so the first thing that we need to do is to check for the ACF and the PACF plots. Now, the ARIMA model, before I come into this, the ARIMA model is one of the um is one of the more popular models for time series forecasting. You do have Prophet, and you do have some other models. Some people use XG Boost, some people use LSTMs. You can use a variety, but Arima is one of the more popular ones for this purpose. And you even have variations of it where you have Sarima, which is Sarima. The S in front of it is just for seasonality. But I won't be going into that because I want to make this video short. Ideally, I should be using it since we can see that this is a seasonal data. You can see that this is a seasonal data. So the Sarima would actually be ideal for this, but I'm not going to go into that. I just need to show you how I use the ARIMA model for this. But there are some things that we can tweak to make things a bit better. Okay, so in the ARIMA model, you have the AR, and that means the auto regression. And basically, what that says is that the model assumes that the current value is dependent on previous values. So basically, if I sold like 5 cookies today, for example, I could say that okay, tomorrow I'm going to sell like either 4 or 5 or 6 cookies because I know that okay, my sales for today depends on my sales for yesterday, and my sales for yesterday depends on the one for day before yesterday, and that kind of thing. So it's more like a linear regression kind of thing. So where you have the thing of tomorrow being dependent on the thing of today, and the thing of today being dependent on the thing of tomorrow, and for that we usually look at the PACF graph. Um, if you want me to give more in-depth explanations of this, I can just put that in the comments. But basically, we'll look at the PACF graph. I'll show that later. Well, in fact, let me show it now. Should give us something. All right. Okay. So we usually use the PACF graph to help us with the AR. Okay. If I forgot to mention this before, the ARIMA model is a combination of like 3 different models, or it's really a combination of 2, but then the I is more of a. I wouldn't really call it. I don't know if I could call it a model. It's more of a factor that helps us with seasonality and the data being stationary. But I'll come to that later. So AR, like I was saying, that's your auto regression, and like I said, it helps with. That's when you look at one data point being dependent on the previous data point. So the next part of the ARIMA model that we look at is let's make this look nice. Okay. The next part that we have is the MA, which is our moving average model. Um, So basically, that makes the it makes the model more robust in the sense that it assumes that the current value is dependent on the error terms. So um, it's basically helps with the errors. It basically helps with the errors because there are some days where it could be cold. In this instance, now I mean this is energy consumption. There are some days where it could be cold in the house and you just don't feel like putting your heater on. You could just decide that, okay, I'm not gonna put my heater on. I don't feel too cold myself. Probably I have a fever and I'm feeling hot and I would like myself to feel cold. Now, that is an anomaly because usually anytime someone is hot, anytime someone is cold, the person puts on his heater to feel warm. But then there are some days where you just don't want to put on your heater. It could be for various reasons. So you could call that an anomaly, and we can refer to that as an error. So that's what this is. And in some cases, let's see, do I have the notebook right here? I think I'll just draw. Okay, let me use my notes. Okay, just to talk about the. Okay, this is another one. Let's take that one away. Okay, let me just draw something. So basically, what the moving average could do is in instances where you have something like this. So now for the fact that you have a lot of up and downs right here, a moving average could make the graph go like this. It could just really smoothens things down, and this is mostly used for stock data. Anytime if you ever try to analyze stock data, you definitely see something about moving average. It's a well known feature right there. Okay, so that's the MA. And then we have our I, which means um, I means integrated. I means integrated. So what basically that means is it helps with the whole differential thing, and in layman's terms, it helps you to make your data to be stationary. Okay, so remember I drew a graph like this before. So this is a data. Let's say this is shows like a trend here, and if we look at the mean, we can see that the mean is not constant. If we look at the mean of this guy here, and this guy here, and this guy here, they are not going to be very similar. So the ARIMA model usually works best when the mean and the variance are stationary, which means the data set should be something like this. Should be something like this, probably on a straight line. Not necessarily a complete straight line, but it should be straighter than this. It should be straighter like my drawing is quite bad here. It should be like this and not like this, basically. So your ARIMA performs better when it is like this guy here. So this is good, this is bad. B, G, yeah, good, bad. All right, so that's what your I helps you with, and so that's it. Those are the three parts, and usually the ACF and the PACF. This is autocorrelation, and these are the lags that we have. What these lags mean, or what these noodle points mean, you might hear them sometimes. Noodle points. I like that name actually. Anyway, so what these lags mean is, for example, now we could say that if a lag is lag 1, then that's the previous day. If a lag is lag 2, then we can say that's 2 days prior. If it's lag 3, and on and on like that. So let's say today is I think what's today? Today is Friday now. So this is Friday at my time. If there's a lag of 1 day, then that lag of 1 day is Thursday. If there's a lag of 2 days, then the lag is going to be The lag is going to be Wednesday. I don't know why I forgot the days of the week there. But anyways, we this gives us an idea of the relationship between a particular point in time and its previous lag, and that's the immediate lag before it. So that's what the autocorrelation gives us here. That's your ACF, and we can see that it goes down. There's a very fast decay, and it rises again, and then there's a decay, which means that this is a seasonal data, and we really should be using Sarima for this, but I'm just going to stick with Arima for now. I'm very stubborn. So we also have the partial autocorrelation, and this is usually associated with our AR parts of the ARIMA model. So partial autocorrelation. So let's explain it like this. Let me give this instance now. If I want to know the relationship between the sales of Wednesday and Monday, what I do is usually I'll look at the sales for Monday, then I'll look at the sales for Tuesday because Tuesday sales are related to Monday sales. And for me to know the sales for Wednesday, I will look at the sales for Tuesday, right? So now I know, so now Tuesday determines Wednesday and um, Monday determines Tuesday. So the relationship, I can now say that the relationship um, between Monday and Wednesday is can be connected by Tuesday, right? So Monday to Tuesday, Tuesday to Wednesday. Let's just look at it that way. I think it's better if I try this. I think I'm saying too much. Oh, I've quit it. Okay. Anyways, um, so instead of me saying that, okay, instead of me saying that the relationship between Monday and Wednesday is from Monday to Tuesday and Tuesday to Wednesday, I could just say that the relationship from Monday to Wednesday is Monday to Wednesday. That's another thing. And that's what our partial autocorrelation is. That means you're actually the relationship from one day or from one value in time to a previous value in time. It's going to look at the direct relationship. It's not going to look at this as a chain, if you get what I mean. So when you look at it as a chain, that's usually when we talk about autocorrelation. That's the day between the relationship between Monday to Tuesday and Tuesday to Wednesday to see the relationship between Monday to Wednesday. But partial autocorrelation, we can say that that's going to be the relationship between Monday to Wednesday. We're not going to consider Tuesday in this instance. So basically, that's what this whole graph is telling you right here. And you might ask me, Emmanuel, why? What's the whole point of this that we are doing? And the reason why we're doing this is because we need to know what some values are, and that's going to be, let's see, over here. Where did I put that one again? It's because of this guy here, something like this. This is the reason why we need to know. But I'll come to that later. So for this we have, so for an ARIMA model we have P, D, and Q, right? So we have P, D, and Q, and basically what that is those are basically the hyperparameters that you have, and those hyperparameters usually help us determine how best to tune our ARIMA model. So what we have is we have P being for the AR, then D is for the I, and then Q is for the MA. So I'm just gonna put the one note back. I think it's better if I just write this down. Okay. So let's say, for example, we have A, R. Oh, forgive my drawings. So you can say that the AR is going to be our P. we can say this is going to be our D, and we say this is going to be our Q. All right. So P is basically the number of lag observations in the model, and we could also call that the lag order. Then the D is going to be, which is our I here. I think it's better if I put it this way. So D is the number of times that we need to difference the data sets, because remember I said that we could have something like this, and every time we try to make it like this, the process of trying to convert something like this into this, we call that that's when we are differencing it. I think that's the word. So we're differencing it, and then MA, which is our moving average, that's going to be our Q, and basically that's going to be the size of the moving average window, and you could also call that the order of the moving average window. So basically it's just like how much of the past error that we want to consider. Okay, so this is the ARIMA model. You're definitely going to have to put these three in, and it might seem like a game of luck, but we do have auto ARIMA, and that one usually finds the best combination of these, but we'll just use some values. Okay, so what this is telling us now is that we need to do some changes, and apart from these two ones right here, this is not meant to be decaying like this. And for those of us that are wondering what this blue thing is, that's 95% of our confidence interval. All right, so most of these are actually meant to be in this. You shouldn't have too many of these shooting out, but I think this is not so bad. But then this whole seasonality thing is not too good. So what we can do is we'll just apply difference to data set, and we'll see. Oh yeah, and I forgot to mention that the p-value is also another thing that's important. And usually we use the stats model library to do this whole thing. We use the add fuller function right there, and we can see that here it's 0.95, and ideally our p-value should be less than 0.05, so that we'll be able to reject the null hypothesis. So we have 0.95 here, so these three indicators are not good. So what we will be doing is we're going to be doing the diff, and let's see, did I import that from there? Okay, we'll be doing the diff of the train sets, and let's see what we have. So now it is a bit more, it looks a bit less seasonal, which is good. So let's see if our graphs are going to be good. Okay, now this is far better. Now you can see that most of these points are now inside the confidence interval, which is good, and our p-value should be better now. It should be better. So we can see it's going down. This is 0.2, which is far better than what we had before, which was 0.9. So it's still not good enough, because we need it to be less than 0.05. Now we need to be careful when we are doing this whole difference thing, because if we do that too much, then we lose a lot of information from the data set. So it's usually recommended that you just do it once or twice and not more than that. So we're just going to apply it again. This is what I applied it to. So remember, we did it once, and this is going to be our second time. Excuse me. This is going to be our second time. So we now have this right here, and let's see if we have something better. So you can see that's still good. That's still good. So now we have something less than 0.05. So we can say that we did this twice. So our D is going to be our D here is going to be 2, and we'll just leave the P and Q to be 1 for this. So we have the stats model library, and we'll be importing ARIMA, and we know that this is going to be PDQ right here, and we're going to be applying that to the train, and basically we'll just be fitting this into the ARIMA model, and we'll be having something like this. Okay, so we have this. So this is basically like a summary that we can see. And let's see. That's a timestamp. The reason why I did this was because I needed to plot the graph, and it was giving me a problem. So I had to do that. So evaluating ARIMA performance, we'll see. Okay, we can see that what we have, the actual data and the fitted values, they are very similar. Small differences, but they are similar. But that's is just to make sure that our model is working correctly. Okay, so what we have now is we'll just be going down, and let's see if we can forecast those values. Okay, so we'll be fitting the forecast and looking at the length of the test set. I think the test set should be about 6. I think it's 6 or so. Okay, so let's see what we have. Okay, so we have the consumption here, the electricity consumption in Romania, and this is our forecast right here, which looks okay. It's not so far from what we have. This right here is because 2025 was not complete, so that's why this goes down too much. So that's basically how we do the whole forecasting thing, and that's how we apply the ARIMA model to do forecasting on a data set. Um, there are definitely other models that we can use. The ARIMA would definitely be a better option in this instance. It's most likely going to be a better option because of the seasonality, but at least the I was able to help us to improve things in this instance. That's the I here. So before we go, we're just going to make sure our model is able to see our evaluation metrics. Okay, so this is the mean absolute error, which is this. This number is big because the numbers are quite big. So it's basically like the mean absolute error. From the top of my head, that should be like 1 over n, then the summation of let's say for example x of t, and let's say x of t minus 1, and then it goes on something like that. I think that's what the MAE is. So we have that, and then we have the mean absolute percentage error, that's 0.16. Then we have the root mean squared error, that's the RMSE, root mean squared error. So this is for the square root here. So the reason why you're probably looking at this as this is quite a large number, and that's because our consumption values are quite large, and this is, I think this is this 1 billion or 10 million? Okay, so this is 10 million right here, and that shows you how large our values are. So that's why we have something like this here. So basically you can apply this to different scenarios to predict consumption, to predict anything for time series. It's even how they are giving me a direct debit for my own electricity consumption at home. So basically, they forecast what I could use over the course of a year, and then they use that to give me a direct debit. They use that to give me a direct debit, and that usually takes some money from my account every month to pay for my bills, for my electricity bill, to be exact. So these forecasting things, they're very, very important. So that's what we have there. And yes, basically this is using the ARIMA model to do the forecasting to do the forecasting of values. And thank you very much for watching. If you'd like me to explain the ARIMA model more, you can drop a comment. And if you'd like to see me use the SARIMA or the SARIMAX model, which is meant for the seasonal data, then you can also drop a comment and I'll make sure to leave another video to dive in deeper. So thank you very much and I shall see you another time. See you.